I'll start with an analogy. I had, back in high school, a very nice physics teacher. And there was this time when we were studying aerodynamics and Newton laws, and he gave us this example. The video was loading. Yes, this is working. Have you seen this bridge before? Does it look familiar to anyone? Yes, I see lots of hands raised. Nice. So the story of the bridge, back in the 40s, they built this bridge that was crossing the Tacoma Narrows in the Washington state, and that funny effect happened. This happened a couple of weeks after inauguration. Already during construction, they saw that the bridge was wobbling in a suspicious way. Eventually, they had to evacuate. There was one car that was left. They didn't manage to remove the car, and unfortunately, inside of the car, there was the only casualty of the whole accident, a dog. Eventually, what you would expect. These pieces of the bridge became a very nice house for the fishes down the river, basically. This was a shock to a lot of engineers. Everybody was shocked. How could this have happened? What did go wrong? What did we miss? Sorry, microphone is moving. And it said, like, if you read the article in Wikipedia, it will tell you that it was like before and after in the history of engineering. It was like a mind-blowing thing to all the bridge engineers. Then World War II happened, so they didn't rebuild a new bridge until like a decade later because budget priorities, you know. So this happened with a wind of 40 miles per hour, and I need to insist that I'm a very strong supporter of the international metric system, but the Wikipedia article was written by Americans, and I'm too lazy to do the conversion. Everybody can find out. But in any case, it's not a lot of wind. So, no, I don't want to. I want to go to the next slide. Next. Sorry, now the click is playing the video again. If I... There, okay. So, before, bridges were like this. Back in Roman times, anybody that knows me knows I love the Romans. Bridges were solid pieces of stone. The force of gravity, in comparison to every single other force, was overwhelming. Like, what was the use case for this bridge? There was a few legions, maybe some merchants. How heavy the legion is in comparison to how heavy the bridge is. It's irrelevant. It's how heavy is a truck plus a fly? It's just a truck, like, doesn't matter. How much wind you need to do anything to that bridge whatsoever? Like, there is no such hurricanes in Europe. But then one day we went to bridges like that weighed just about the same, and they spun dozens of times longer. They are flexible. They carry loads that sometimes can be as heavy as the bridge itself. You know, back in the Roman times, there was a legion with what heavy armory they had. And, you know, these days we have really heavy armory, as we have all seen in the news. So it's a completely different use case. And forces that did not make any difference whatsoever, like the weight of the users or the wind or all the other stuff, now they change completely the rules of the game. So why am I talking about this? Let's give you an example that you will find more familiar. This was computers back in the days. This computer, just like the Roman bridge, had fewer use cases, very few users. Users were usually very proficient, and I don't know, like you could even punch that computer and probably you would break your fist and not the computer. If I punch this one, the presentation is over and my boss would be sad. So completely different century. Then we went to this stuff that you all know it exists, and does anyone really understand the entirety of it? Like, we have had to specialize so much in every single piece of what a new computer looks like that there is no such person that knows all of it. And they are less stable. There are new forces that can play a different role. Like, for example, the old computers, they have specialized power data centers, so if the electricity goes off, it always works. But in the new one, sometimes you have an update, sometimes there is power off, so you just migrate to a different data center. It's a lot more unpredictable. So, again, interactions, the traffic capacity, the amplifying factor. So the use case, as I said, we went from one specialized user to sky's the limit. how much traffic the old computer was handling and the new one is handling, like in comparison to the bridge. Amplifying factors. The wind that blew this Tacoma bridge, the thing is that it's a complicated explanation, as me in the corridors we have so much time, but basically it resonated with the materials of the bridge and it amplifies the movement. So a wind that would produce a little bit of movement would then amplify and produce a lot more movement until the bridge was out. So amplifying factors. You probably know this about like compression, or Memcache had a famous vulnerability a few years ago for amplifying factor. So let's get to some terminology. Enough about bridges, because this is Lambda days and not engineering bridges. What is a framework? Let's go word by word to the title of my presentation. Here you have a bunch of copy-pasted descriptions from dictionaries that you can read while I say something else. The most important line is the last one: a system of rules, ideas, or beliefs that is used to plan or decide something. And what is a model? Basically, a model is theoretical, while a framework is empirical. We can have a model of the bridge, but we don't have a framework of a bridge. We have a framework of how to build the bridge. We have a framework is a set of tools. The model is the representation. This example, another question for you in the corridors, is of a model of the inverted catenaries of the Sagrada Familia. If anybody has been in the Sagrada Familia, this is displayed in the museum. It's a masterpiece of engineering. I also like Gaudí very much. As me in the corridors, this building will be finished any day now. I welcome all of you to visit sometime when they finish it. Testing. We all did tests in school, right? And keep doing them these days. It's basically like we want to prove that the system does what it's supposed to do. Like the kid knows the mathematic tables, or the adult knows, I don't know, the Kings of England, or whatever. Our program doesn't have bugs. And what is load? Mass or quantity of something taken out, carried, conveyed, or transported. This is what Newton, coming back to the physics teacher, would love to call forces. Work, sorry. So what is load testing? Testing that under a certain load, the system behaves how you would expect. There are three kinds of testing. One is regular performance testing. At minimum load, we just want to verify how fast a certain algorithm, a certain program is. There is load testing, for the redundancy of the name, where we check how the system behaves in the edge at maximum capacity. And then there is stress testing, where you kill it. You intentionally give it more load than it's supposed to handle in the service where in the server where you deploy it, to see it die, to see how does it die gracefully or not. Do you have like back pressure mechanisms? Again, you will test these kind of mechanisms. So, load testing framework, again, a system of tools and ideas to apply loads in all the possible ways the system allows. And again, coming back to the Docker containers and the cloud of computers, you would never imagine what are the use cases. Like back in the days, it was a one specialized guy in a mainframe. Today, ask your grandma using the internet. Nobody knows what people are doing. So we have, not yet, we have one advantage over bridge engineers. Again, this is Lambda days and not engineering bridges. That we can duplicate, we can replicate our service. We can just make a copy and hundreds of it and deploy it everywhere and kill it and see how it does. The bridge engineer would be very jealous of that. He doesn't have two chances. There is no way he can build two bridges to test one until it breaks. It's too expensive. Nobody does that. But we have that privilege. So, all the forces that can be applied. We had the bridge. This is like the half of it, more or less similar to the one presented before. We have, of course, gravity, which, if you may have studied physics, you may remember that the arrows, they relate to each other, and in the end you can calculate how the forces move with Newton laws or more complicated things these days. It gets really crazy when you start adding dynamic forces like wind and you get into differential equations. It's a crazy world of interactions. You have arrows of a size applied in a place with a direction, and then they interact with each other. So similar idea, more or less, is when you deploy a service, say a website, and you have the internet, everybody can use it in different ways, with different frequency. Say you deploy a game and some gamers are a lot better than others, and some people click at the speed of light than some others are learning. Users are going to be very different. They are going to interact with each other. So what we want, in the analogy, is to like the arrows. We want an arrow that knows where to go, in which direction, how big, and knows how to interact with the others. This is where I'm going to come to the other part of the title of the presentation, the actor model. Let's say that each one of those arrows is a self-deciding program. It's independent. The program knows what to do, where to do it, how to do it, and how strong. But then you want to have millions of them that move, because, again, in the Roman bridge, the wind that is a dynamic movement still doesn't make any difference, so you can just discard it. But this time, users are all different, so you cannot discard those forces. You want those forces to move, to interact with each other, to synchronize if they have to, and to attack your service in every possible way. So that's basically the actor model. The man in the picture is Carl Hewitt, the guy that coined the term actor model. He died last December. And he argued that basically actor is, as explained here, that self-deciding program that has these properties. It can send messages to other actors. It can create new actors, and it can choose how it's going to behave when it receives the next message from a different actor. It was probably mentioned at the beginning, or it was on my slide. I work in Erlang Solutions, Erlang, actor-based language. Some of you may be familiar with it, some others may not. Some of you may be familiar with actor frameworks in different languages, like Akka or Tokyo in Rust, for example. The idea, and I'm going to simplify very much in case anybody doesn't know what is the idea of an actor. I'm sure you all know object-oriented because that's like every programmer heard about it once in their lives. You know functional programming because that's Lambda days where we are. The idea is that in a language like Ruby, for example, you can do whatever, dot, name of a method. Maybe the compiler will tell you that is not correct, but syntactically it is. That's the language. And it may crash at runtime if the compiler doesn't complain. Similarly for Lisp, you can do whatever, parentheses, and syntactically correct. Maybe the compiler will warn you. Probably it will crash at runtime if it's not correct. In a language like Erlang, you can do whatever, exclamation mark. Often the compiler will complain if that is not a process identifier, which you cannot forge, or is not a globally registered name, which you can, but you need to register it first. But it's syntactically correct. Everything is an actor. Everything receives messages and acts to those messages and creates other actors. So, framework given. Let's go now to the meat of the presentation. I work in a project called Mongoose IM, which is backend, messaging backend. Some people here are familiar with it. There are some coworkers. I see some old customers of mine, so you have all heard, the few of you, about Mongoose IM. It's an XMPP-based, customizable, scalable, not the presentation for advertising Mongoose IM. That is XMPP-based. And in XMPP, I don't know why, for whatever beautiful reason, all examples are given using Shakespeare's quotes. So when it comes to messaging, Juliet writes to Romeo from the balcony in Verona. It's a fantastic RFC to read. It's fun. So lots of years ago, in my team, even before I joined, we created a tool called Murder of Crows. If you have not watched this movie, just do yourself a favor and watch it. Apart from being a fan of Gaudi, I'm also a fan of Hitchcock. Crows are animals that eat the dead bodies of other animals that died. I don't remember the word for it in English, never mind. And a flock of this animal in English is called a murder. So we want these animals that are going to attack you, like in the movie, and they are going to interact with each other, interact with you, see how you get scared. They are going to try to make you run. They are going to make you realize that there are forces that now matter. In the program, you started with an init, where you initialize like your database, if you want to store some metrics about the test that you're doing. You then start all the actors that you're going to need, and then you can add more and more incrementally. And you run the scenario locally or distributed. I'm going to give later an example that is going to be locally because we have so much time, and everybody knows distributed is always more complicated. So things that you would want to do with your actors, you want to throttle them, just to see, slowly test, like you have a website and the users connect 100 per minute, 1,000 per minute, and you slowly see how the website, like when the website reaches the edge. So you want some mechanism to throttle them. And you also want maybe a mechanism to tell one actor to throttle the other. You will also want to coordinate them. As I said before, the arrows interact, and at the end you have these funny differential equations of the final force. So in this case, the actors are going to send messages to each other, and you would want a mechanism to group them, to choose a few, and so they do together a special action, for example. And yeah, those, you want the throttle and the coordination. And now I'm going to give you an example. Hopefully, lots of you have seen this in the corridors. If you haven't, you're more than welcome to go and play. You can scan this QR code. It's in the corridors, in the stand for Erlang Solutions. We can give you more of these QR codes. The game looks like this, if you have seen it. You may have played this game in actual cards. For copyright reasons, this game here is called Monomatch. So now I want to check how this game works. How many of you can play before the server where I deploy this dies or cannot respond to you sufficiently fast and the game doesn't feel like a good experience? So a little bit of code. We have init, where we will start a coordination plan that I will show in the next slide, and two throttles. One is users connecting. So first of all, I want to maybe check how fast the HTTP service can start the connections and then respond to them. And a second throttle to how often the users can create a room and start playing, because you first connect, you get the website. So that's the first thing that I want to throttle and have a look. And the second thing is when you create the games. The coordination plan is going to look like this. I get a bunch of configuration flags, and then I get this tuple, the number of users per game that this is configured, and what those users are going to do. I get in this function the list of users. I choose the first. I tell to a throttle mechanism to, when the throttle allows, tell that user to start the game with all the others. So I will send this user a message that says create and start the game, this type of the game with all the other players, this deck size, and this number of rounds. And as the users start, the first thing that they are going to do is wait for, like, the throttle allows me to start the HTTP connection and the WebSocket. Once that is done, I will just check the configuration, how hard do I want to play, and add this user to the coordination mechanism that I said before. As they are starting, the coordination had this configuration flag that said 6 users. So every time there is 6 of them, then the coordinator is going to do the action that you saw before. To the first one, it will tell him, you create the room, tell the others to join, start playing. And then this code will go into a state machine, code that we're not showing, and will start playing. Here I started a very simple example. Here I started, how many was it? 100,000 players. And they join rooms of 6. And we can quickly see, we have, like, I've been just told that we have 1 minute, so we can see that in the service, the users can connect to the HTTP channel very fast, but they are, the part that, the code that creates the rooms is not really well concurrently implemented. This was on purpose. And so even if the throttle is allowing to create more rooms, the service is actually creating less of them. It cannot keep up until there is less. A different coordination plan, when I get the list of users plus 1, so if I had configured 6, now I'm going to get 7, divide them in 2 groups of random sizes. You can see rand uniform, and we'll choose randomly a room of like 3 users and another one with 4 users. They will do exactly the same. And here we get in this graph below, for example, the number of rooms that are, the number of games that are created per size of the room. Finishing here, this is code, this is the repository. It's called AMOC. There is an important pull request with a lot of changes that I have made that my colleagues are aware of. hopefully will be merged soon. Over there, we have an example, a repository with examples for how we load test our messaging backend if you want inspiration for how to create your scenarios. And that's all from me. You can find me by that name. And if you see whatever with that picture, it's probably me. It's my picture everywhere. That's all. Thank you very much.